Hello, welcome to a third video in representations of data. In this short video, we'll be looking at cumulative frequency diagrams. So a cumulative frequency is used to estimate measures of location from grouped data. Let's illustrate this through the following example. So the table below shows the masses in kilograms of 120 Coulter pine cones. So, we are asked to draw a cumulative frequency diagram for this data. Cumulative frequency also means the running total in more everyday language. So cumulative frequency is just a technical way of saying the running total. So if I look at this data set, how many have a mass of less than 1.2 kilograms? It would be 7. How many have a mass less than 1.4? Well, it's those 18 in this class and plus the 7 before to get a total of 25. And in a similar way, we can do the cumulative frequency for each of those classes. How many have a mass less than 1.6? Well, we add 34 to a previous total to get 59. How many have a mass of less than 1.8? Add 41 to get a total of 100. Similarly, for a mass less than 2.0 kilograms, we have 115 pine cones. And lastly, we have 120. So when we draw this cumulative frequency diagram, and you'll see there's one I prepared earlier, there are 2 points I want to emphasise. When we label axes, we've got cumulative frequency and we've got mass labelled as so. But look at this point here. It's 1.2 and a cumulative frequency of 7. Notice how we always plot the upper boundary of the diagram. We always plot the upper boundary for each class width. So I plotted 7 and 1.2. Let's verify that with another one. This coordinate here is the upper of 1.5 and 25. And in a similar way, I've plotted all of these other points as well. Okay, again, a skill that perhaps you might have seen at GCSE. Let's see why this is a valuable thing to do. So if we wanted to estimate the median mass, we would normally use interpolation to do that. We would look at our values, we would use interpolation to find that value. However, a cumulative frequency diagram gives us another method to estimate the mass of the median. We know that for continuous data, the median is the number of data points over 2 that data value. So in this case, it would be the 120 divided by 2, the 60th data point. So we can use our graph to go across and then down. And then perhaps unsurprisingly, I get a value slightly bigger than 1.6. I might estimate it to be 1.61. And then this value, this method of estimation can also be used to find the interquartile values. We would say Q1 would be 120 divided by 4, the 30th value. Go to the graph and go down. And you might get a slightly different value in your graph, but I'm getting about 1 point, well, I would say it's perhaps, yeah, pretty much exactly 1.44. And I can also find out the upper quartile, which in this case, 3/4 of 120 would be the 90th value, which would be specifically for this. Across to the graph and then going down. I think I'm getting, yeah, probably about 1.72. And then I can work out the interquartile range by subtracting those values and doing the calculation. I believe, what would that be? 0.6, 0.22, 0.28. And this method of estimation can be, in fact, used to work out any percentile. In particular, the 10th and 90th percentiles. Okay, so, apologies for the board work here. I'm going to continue this. The 10th percentile, that would be the 12th value. Oops, gone too far. And down to the graph, 1.26 I am getting. And then for the 90th percentile, well, 90% of 120 would be 108 value, which in this case, using my diagram, I'm getting a quite nice value of 1.9. So I could say that the interpercentile range of those values, interpercentile range would be the difference, which would be, in my case, 0.64. And I just want to emphasize that this method has a flaw of being slightly inaccurate. I've really relied here on that blue line of best fit. And there are lots of lines of best fit I could have drawn through this data set that connects each of those points. So there will be small inaccuracies or small differences based on our graph here. I would expect you to get slightly different values for most of those points. Okay, and then in part D, we are asked to draw a box plot to show this data. And it's a nice visual way from taking this two-dimensional graph of our data set and putting it into a one-dimensional plot. So, assuming that there's no outliers, we can condense this two-dimensional image into a one-dimensional box plot. I can plot our minimum value, that lower bound of 1.0, our max value of 2.2, and then I've got the lower quartile here, kind of extending this line down, and in a similar way, the upper quartile, and indeed the median. Apologies, let's fix that. And in such a way, we have created a box plot of our data set. And I'd like to just pause on that image there of the two-dimensional graph at the top being kind of squished into a box plot which retains the key features of the maximum and minimum values, the interquartile range in the middle, and indeed the median as well. Okay, we're now at the stage in the booklet where there are some exam questions for you to practice. I'm going to leave these blank and we'll have a look at the answers in class. Exam question 2 as well, I would like you to have a go at. And I'm going to stop the video here.